Yes, so I want to reinforce what Richard just said. I mean, I'm going to be talking about what I know about, which is brain stuff, but I really want to be integrating this into what you guys are thinking about. And in order to do that, I'd love your feedback at any point. Just, stop me if I'm being too brain confusing. And if there are connections you want to make with anything, feel free to pull me over. This is adapted from like what was a 22-minute talk or so. And so there should be plenty of time and space for that. Okay, yes, and I've chosen the hopefully evocative title, the shared predictive roots of motor control and beat-based timing. So what I want to talk about is hopefully going to link the ideas of beat-based, the fact that we experience the beat in music and the way we use our bodies. Giving a little bit of background on me first. My background has been somewhat wending. I got my doctorate in math and statistics, but worked with a professor who focused on neural modeling using dynamical systems. So I was in brain land right away. During that time, I was also working as a semi-professional musician. So I'm a fiddler. I play a lot of klezmer. I play traditional American and Celtic music. And I also became a guitarist during that time. And I think at the height of it, I would be playing maybe a gig every other week or so, every other weekend. So I was thinking a lot about music, but wasn't bringing those together until later. I got a postdoc position at MIT a few years ago, researching autism and prediction. And I was interested in that because what they were going to be looking at included metronomic sequences and sort of prediction of rhythms and when auditory events were going to happen. And that connection to music was very exciting to me. And around the same time, I was setting up this collaboration with Ani Patel, a professor at Tufts in music psychology. And working with Ani has sent me down this wonderful path where I got to bring together my interest in the brain and my interest in music.
Jonathan, can I just ask you, can you check if someone is trying to get into the session?
Oh, yeah. Let me double check. Participants, I think not. I think something would pop up now.
Okay, good.
Yeah. All right. Oops. And now I've skipped a slide. One moment. Go back here. Outline. Yes. So first I'm going to give some background on beat-based timing and what I even mean by beat-based timing in the brain. Then I'm going to present step by step a hypothesis for the role of a specific brain area called the supplementary motor area, a part of the cortex, and its role in beat-based timing. And my approach to that will be to review its function in motor processes and then extrapolate that to try to understand what role it might be playing in beat-based timing. Then I'm going to take a few slides to try to bring together those two roles and try to understand them in the same language, the same framework. In other words, to unify the perceptual function, I meant to say motor and perceptual functions, to unify the motor function and the perceptual function of that brain area, and then loop in one more brain region called the basal ganglia. This is following along with my recently published work with Ani, called How Beat Perception Co-opts Motor Neurophysiology. But since we published that, I've already done a lot of reframing and rethinking, so this will go a little beyond that. So auditory rhythm perception. I'm going to play a stimulus. You guys have maybe heard things like this before, but you can just listen for where you would tap along if you were to tap steadily along with it. Oh, and wait a moment. Actually, I want to make sure I'm optimized for sound and video. Yes, okay, good. Let me start it one more time. Yeah. So what we've got here is a sort of classic beat-based stimulus where people will perceive a cyclic structure underlying this, and they would tap at these positions, which often line up with the clicks, but sometimes do not. You have some beats or tap positions where there's no click, some clicks that don't align with beats. In other words, the sense of a periodic pulse or beat is an internal construct. It's something that we perceive, that we superimpose on top of this rhythm, and just perceive it intuitively. But in this sort of natural intuitive process of hearing that cycle, we are maintaining a sense of the instantaneous phase of a cycle. Where are we in the progress from one beat to the next? And we're also maintaining a tempo. And we're recognizing those in some way and then maintaining those percepts throughout the listening experience. And we use that sense of instantaneous phase and tempo to anticipate when events are going to happen. And we can also use it to plan actions. If we're tapping along, humans are, of course, very good at tapping along with that beat very accurately and even tapping slightly ahead of the clicks that are associated with the beats. So these are the things I'm sure you guys are familiar with. And our sense of the beat is robust to timing perturbation and to a certain amount of structural complexity. So we can hear things that are complex and extract a beat from them, and we can hear things that are even not perfectly rhythmic, and we can still produce the sense of the beat. So as a first step linking auditory rhythm in the motor system, I want to just note that there's a few different ways that the auditory rhythm interacts really powerfully with the human motor system. My actual first connection with this was from personal experience, where as I played guitar to accompany fiddlers and things like that, I would the way that I moved would strongly influence my quality as a rhythm player. And so I would sometimes in between sets continue to move my body, which made my tempo much steadier. There were clearly some profound connections there that made it important for me to use my body in some way as I was keeping rhythm. Of course, people seem to spontaneously dance to music across many, many different cultures. But one connection I want to highlight is also a connection with Parkinson's disease, in which people will have trouble initiating steps, they'll have trouble walking, but when listening to rhythmic auditory stimulation in the form of a metronome or in the form of rhythmic music, you see Parkinsonian patients' gait improve dramatically. This can be used for rehabilitation, or it can be used in real time and just making it easier to walk right now by listening to music. So here's a video of somebody with Parkinson's disease struggling to walk fluidly, showing freezing of gait, difficulty initiating another step. But when they turn on some music, you can walk much more steadily and walk along with the beat. So, I think from all of these different perspectives, there's clearly a profound connection between listening to auditory rhythms and how we use the motor system. When we start scanning the brain, when we do fMRI studies on beat perception, we find that even in non-movement related beat perception tasks, where we're just listening to beat-based stimuli, maybe trying to make perceptual judgments about them, we see a lot of motor-related areas activated. So we see supplementary motor area, which actually encompasses these two areas, supplementary motor area and pre-supplementary motor area. It doesn't matter. I'm going to be talking about them as SMA, or supplementary motor area. It's on the cortex inside this middle fold here, or right between the cortices. And the basal ganglia is the other motor-related area that's consistently activated by beat-based perceptual tasks and just listening to beat-based music or stimuli. And the basal ganglia is associated with initiating movements and selecting movements. And in particular, the subregion called the putamen is associated with those things and is activated by beat-based tasks. We also see premotor cortex, out here further out along the cortex, which is associated with motor planning, and also auditory and parietal cortices, which are a little less surprising because we're listening to things. Cerebellum seems to get activated by some tasks, but I'm not going to be focusing on that very much, partially because it seems to be equally or more activated by non-beat-based rhythms, and partially because it's more activated by actual motor tapping along, but not as much by perceptual processes. And so I'm going to be focusing largely on this covert beat maintenance and covertly keeping the beat and listening to it. Two important notes here. One of them is that this is mostly taken from fMRI data, which means that while we get this wonderful spatial resolution, we really can't see what it's doing from moment to moment and from beat to beat. which is too bad. And we really lack that kind of high-dimensional, time-resolved data in humans that can specify regions. And when we do get that data, it's from animals. And most animals don't seem to interact with the beat in music like humans do, though there's a few exceptions that Ani Patel has been studying, including parakeets and a few other animals. Okay, so this raises the question of what are those motor-associated areas doing when we're just listening to something with a beat? Why are we activating the motor system at all? It's been widely hypothesized that the motor system plays some kind of active or causal role in these timing processes, that it's actually serving some essential perceptual purpose that is related to timing. More recently, people have proposed that maybe what we're doing to time intervals in a rhythmic sequence is to simulate actions. So something like imagining moving and moving with a certain duration or cycle might be serve a timing function, but that's very underspecified. I think we know from experience when we're rocking out to a beat, it's not like we're imagining moving a hand necessarily or a specific part of our bodies. We can do this all very covertly without thinking about a specific body part. And so it's not at all clear what simulated action really refers to in these ideas. And so, as I mentioned before, my approach is to look at the motor functionality of these regions and to try to extrapolate from that, rather than coming in with this idea that we may be simulating action. I want to say, all right, well, what are these motor areas doing specifically when we are moving? And does that perhaps have some important bearing on what they might be doing when we're just listening? Supplementary motor area. The first set of neuroscience results I want to review here are these recent results looking at the supplementary motor area in primates when they're doing things that are cyclic actions. And so what's been observed is that if we take the firing rates of a whole lot of different neurons in the supplementary motor area and we graph them all over time in this very high dimensional space, one dimension for every different neuron, it's very hard to visualize that, but we can boil it down using some statistical techniques to try to graph in like a three-dimensional space what this whole group of neurons is doing as they increase and decrease their firing rates. And when we do that, we see something that looks a little like this. So here's a monkey that is turning a crank. So it's cyclically turning this crank, and it's cranking a background by him. This thing is scrolling as he turns the crank. And what we see in this reduced dimensionality space where we're graphing the firing rates of all these different neurons is loops. Every time he turns the crank once around, we see firing rates of a large group of neurons decrease and then increase again, and firing rates of other groups of neurons decrease and then increase. And what this all sort of adds up to is one loop in this firing rate space for every turn of the crank. And then also some progress along another axis. So there are some neurons whose activity may be gradually increasing or gradually decreasing over the course of multiple turns. And so this representation, what happens here can be thought of as an abstract representation of the progress through that action. And so the loop itself represents the progress through a particular turn, and its gradual steady progress across the space also then can be used to represent its progress through the scrolling background. So it seems like in this task in particular, the supplementary motor area is carrying firing rate information that represents progress, and in particular cyclic progress, but also linear progress. Here's another task in which we see something similar. In this one, a monkey is listening to a click track and tapping along. And it takes a lot of training to get monkeys to do this. They're not as good at it as humans are, but we can get them to do it. And then they continue to tap after the click track stops. And what we see in the same area, supplementary motor area, in the same sort of reduced dimensionality space, is that large groups of neurons will increase their firing rate and then decrease again in time with the tapping. In particular, in this case, we also see that even when the monkey's finger is just waiting, and is not actually physically moving, we still see this cycle continue through that period, suggesting that this is a very abstract representation of progress and not just attached to a particular set of motor commands. So yeah, I think, and this is sort of the groundwork. These observations are the groundwork for what follows. So if you've got any questions about what I'm talking about here, please let me know. The hypothesis that I want to put forward is that in supplementary motor area, the same way that it seems to represent progress through an action, it may also represent progress through a cyclic structure in listening. And so as we listen to this click pattern that I played for you before, the supplementary motor area firing rates may be playing out to represent phase and progress through that auditory stimulus. And again, this is during pure perception, so this would not be necessary to be moving along. You might see something like this. I've got an animation here, and as I play this click track, I'll show what the supplementary motor area firing rates might be doing. And so you see one loop for every perceived beat, for every cycle of a beat, and also some kind of linear progress across the space as we move from the beginning to the end of the rhythm, or through some slower structure in the rhythm. So this is sort of the structuring idea around this, which is that the supplementary motor area is tracking progress through action, but also tracking progress through perception, and in this case, through auditory rhythms. And we might not actually see this in monkeys because humans are so attuned to auditory rhythms and so spontaneously ready to engage our motor systems with it. I can talk more at the end about why neurally that might be. I don't have a very clear answer for that, but so this is my hypothesis as to what we would see if we looked in human supplementary motor area with the same density of recording as we are with monkeys. So this raises the question of, like, how would this kind of representation be established? If we're not actually moving ourselves, how are we extracting this beat information and creating this pattern of activity in the supplementary motor area? So looking in monkeys, there's, from the same task I was talking about before, this entrained tapping task, there's evidence that the supplementary motor area is building a representation of action based on the timing of sensory events. So in this case, while it's synchronizing tapping to visual and auditory cues, a whole lot of cells in the supplementary motor area were directly time-locked and apparently driven by the pacing cues. So even though this region of the brain came to represent action as it continued the tapping, it started by being very much driven by the clicks or the visual cues. And we can see this in this little graph here. Over the course of tapping, the number of cells in that region that were directly time-locked and driven by the sensory clicks started as a good portion of the cells and decreased, and the number that were locked to the motor output increased. And so this starts to paint this picture of this brain region that is starting as getting information from perceptual timing, but then using that to start to construct this picture of where is the monkey in its action. And so starting to sort of conflate the perceptual timing and action timing and moving from one to the other, moving from a mechanism of just taking information in and building a representation to then continuing to represent the monkey's action cycle. Take a break for a moment. And so extending this to ideas about rhythm tracking and supplementary motor area, the hypothesis is that SMA is integrating auditory cue timing to inform its estimate of phase and progress through rhythms in the same way that it is integrating cue timing to start to build up this representation of action phase. And this would have to be based on associations between specific event times and a specific position in the cycle. So of course, the most salient one might be associating an event happening on the beat, at one specific point in the cycle of the beat. But there also might be associations that would associate events happening halfway in between two beats, having an even subdivision. And that too could be used to inform the position in the cycle. So a next question is, what functions could be served in the brain by estimating phase in action and in listening? And so there's this whole other literature on the supplementary motor area in humans showing that it's involved in two different tasks, both enhancing and suppressing sounds that are generated through one's own actions. And so this is task dependent. So if in some tasks you may need to specifically hear feedback, in others you might need to ignore it. But in both of those types of tasks, you see that the involvement of the supplementary motor area. And so this starts to come together into a picture in which, well, hold on. So sound prediction in general is thought to be moderated by models in the premotor cortex, this other area that was active in beat-based listening. Which then inform auditory pathways what to expect to hear at a particular time. And those predictions are informed by some estimate of your motor state. And so the involvement of SMA in enhancing and suppressing self-generated sounds may look a lot like this. SMA is making an estimate of the phase or progress through some action, informing the premotor cortex of where it is in the progress of this action. And then the premotor cortex is then sending a signal to the auditory pathway saying, now you should expect a sound to happen right now, and right now, and right now. And then that can be applied for enhancing or suppressing the perception of those sounds. And so this may be very much what the role of SMA looks like in rhythm tracking, in keeping the phase in a beat. SMA can send its estimate of rhythmic phase or progress through a longer structure down the auditory processing hierarchy, where it can be used to predict and to suppress or enhance signals from the auditory cortex. And then bringing that together with this idea I proposed earlier that that phase is informed by the timing of auditory events. The timing of auditory events may be forwarded up through this hierarchy. And in particular, auditory events that are not well predicted may then forward up through this hierarchy and be used to correct the estimate of phase in the supplementary motor area. And I frame it in this way because this is really consistent with a set of ideas called predictive coding or predictive processing. In that, that's become an increasingly popular way of looking at the function of the brain as a whole and the structure of sensory systems in general, in which predictions of what's going to be sensed or taken in go down a hierarchy of cortical regions, and prediction errors, things that aren't accurately predicted, go up in order to adjust those higher level understandings and inferences. And so this would be an example of a predictive processing hierarchy. So as a next move, I want to take a sort of a detour into predictive processing, and to start to explain how the motor functions of SMA and its perceptual functions could be more fully unified. I'll just take a moment of awkward wait time here in case anyone has any questions about this sort of way stage of this hypothesis and what I'm talking about here. Wait time is fun. I spent a little while as a high school and middle school math and science teacher, and learning to wait for questions until everyone feels awkward is a really important teaching skill. So looking at this idea of predictive coding and processing more carefully, I want to sort of outline what this all says. According to the predictive coding account of sensory perception, higher areas of cortex, the higher sensory regions, higher visual areas, etc., represent inferences about the state of the world. In the case I've been talking about, those are inferences about what the phase of the underlying phase of a rhythm might be, which is something that's projected onto the world and not sensed directly. And then descending connections from those to the lower sensory regions carry predictions based on those inferences. So what are you going to sense based on what I think I understand about the hidden state of the world? And so those are these green connections from the representations of these about the state of the world that then formulate predictions. And then the ascending connections going up represent prediction errors. So E, these little units are calculated based on those representations. How wrong was I about my predictions as things come into my sensory system? And those ascending connections then report the prediction error. Prediction errors lead to adjustments of inferences and predictions at every level. So if you sort of squint, as I mentioned before, this looks like a predictive processing hierarchy. But I think it may be more intimately related to this extension of the predictive coding idea called active inference. And so what active inference says, this stems from the observation that if you look at laminar or topographic or physiological properties of the motor system, the same principle may be operating as in sensory systems. So there may be descending connections in the motor system. So this is from motor region 1, a motor area of cortex, down to our effectors, our actual nerves that control our muscles. Descending connections may actually be not so much carrying commands to our muscles, but carrying predictions about what we're going to experience proprioceptively. What we will experience, what it will be like to have our arm contracted. And those predictions then may be fulfilled by our motor neurons. And so by predicting that my arm is going to contract, as a result of predicting that vividly and powerfully, my arm then contracts.
Jonathan,
yeah,
can I ask
sure.
a question? You were looking
Absolutely.
forward to a question.
Yeah.
Could you go back one slide?
Sure.
So this picture, I can imagine how it works in the case of a simple tapping task, if someone's simply tapping an isochronous rhythm, right?
Mm-hmm.
And so they have to keep in time with the rhythm that they're hearing, and they either get too fast or they get too slow, and then they get feedback, which gets them back onto the exact timing. So my question is, what's a non-rhythmic task? Can you give an example of something which is not musical or non-rhythmic?
Absolutely. Yeah. Sure. So in for instance, if there were an occluded object, I saw something moving and then it was hidden behind a screen, then I would maintain a representation of where that object is in a higher region of the sensory processing stream, and it would make predictions as to when I was going to see it again. Or in a totally non-dynamic case, I could just maintain a representation of what I thought somebody's mood was, which would be not directly sensed but informed by little things that they said, and this would be sort of a much higher region of cortex outside maybe the sort of a primary visual stream, but I would maintain a representation of that, and that would lead to then these predictions about what kinds of things they were going to say, how they would react to my own actions. So this has been applied across lots of different domains.
Thanks.
Sure. Right. So the idea of active inference is applying this to the motor system and saying that actually our motor commands are really just descending predictions. All of them are telling us that we expect to proprioceptively experience a certain thing, and those predictions, unlike in the sensory stream, are actually fulfilled by our moving to correct those prediction errors. If I expect myself to have contracted my arm, but I have not yet done it, my motor effectors will take care of that and resolve that. But we also have ascending connections that convey prediction errors. So for instance, if I expect my arm to contract, I try to do it, but I accidentally hit the table, then there are certain prediction errors that I can't resolve just by continuing to contract my arm. And in that case, those prediction errors need to be sent back up to these higher motor regions to adjust their model of where my arm is in space and what I should be experiencing now. And so this idea of active inference then extends predictive coding into the realm of motor control. This is a big fancy picture. We don't need to parse the whole thing, but the important thing is to understand that on the left, we've got sort of a classical picture of motor control, which involves lots and lots of feedback loops. And on the right, we have a very similar picture that just reinterprets a lot of these feedback loops as descending predictions and ascending prediction errors. And so a lot of this active inference thing is just a new way of understanding a lot of connections we already knew to be there. But it also includes some new connections that have been observed. And so there's research that goes into trying to fully characterize this active inference system. How can we understand motor control fully as a set of predictions that are then fulfilled, but also updated through prediction errors? All right. So bringing these ideas together, suppose we are doing active inference, we are controlling our body, but we are not only using proprioceptive feedback and making proprioceptive predictions, but also making auditory predictions and using auditory feedback to control our actions. So here, SMA can represent an inference about the phase of a cyclic movement, like I've been outlining before. The predictive phase can be sent down to motor regions, and can be updated based on the how wrong my estimates of phase and progress were in my own. Actually, sorry. Let me start over for a moment. So if I'm making a cyclic movement, then SMA could be sending an estimate of phase to motor cortex, which is setting the time course for the motion. And as that then gets passed down to these motor effectors, my body is now moving in order to fulfill those predictions that I am at a certain phase in my action. But if I am slightly off from that, and my proprioceptive feedback tells me that I'm a little off from what I expected, I can also use those errors to update my sense of the phase of that cyclic action. So we've got this sort of this bidirectional process where an estimate of where I am in my action actually causes me to be at that spot in the action. But errors in that can also be then used to correct my estimate. And so I've got this sort of two different places that can adjust. One of them is my estimate of the phase, and one of them is the actual motor effectors that can then adjust to make sure that those predictions are true. And at the same time, SMA can be informing predictions of what kind of sounds I'm going to hear as I make that action. And so its estimate of phase and progress can be sent to this premotor cortex area that I was talking about before, which informs these auditory pathways of what I should expect to hear as a function of where I am in my action. And errors in those predictions can also then be used to update my estimate of where I am in my action. And so this then sort of brings these two things together. This is saying that SMA is both predicting my proprioceptive experience of a cyclical action and being updated in response to errors in my own motor feedback, and being updated in response to errors in the auditory feedback that I get. And so it's using as much information as it can to keep as accurate a representation of where I am in my action as possible. It's using proprioceptive information and it's using auditory information. And as a side note, I think that its extensive use of auditory information may be the key point in the difference in why humans are so good at this. My hypothesis is that other animals actually don't use auditory feedback to the same extent that humans do in order to control our own actions and adjust them. So what does this look like in something like tapping? So if I'm tapping isochrenously, I'm not even listening to anything, I'm just tapping cyclically, then SMA might inform both my motor cortex and also premotor areas that I should be near the end of the cycle of a tap and getting ready to tap now. My tap should be very close in time. And if proprioceptive input or auditory input tells me that my tap is actually running late, that can then be used to update my estimate of where I am in my tapping process. And then over here, the motor cortex is using that information about the phase of my tap cycle to make very specific predictions about what I'm going to feel from my finger, its position, my proprioceptive experience. My motor effectors are then using that information to actually control my action, to keep lowering the finger, and sending any errors up this processing hierarchy in order to then inform the motor cortex about the fact that my finger is not as low as I expected it to be, which can then inform the supplementary motor area that, wait a sec, your phase is not quite accurate. And I can be using the auditory feedback in a very similar way. Premotor cortex can say, I should hear a tap pretty soon. Auditory cortex can say, oh, didn't hear it yet. And premotor cortex can say, all right, SMA, you need to adjust. So if I'm listening but not acting, then I have no particular proprioceptive expectations. And so we can sort of cut this whole region out, but I can still be using the auditory side of this in exactly the same way. The prediction that I'm nearing the beat produces the expectation that a kick drum should happen right about now. And then the error that there's no kick drum could then be used to update my estimate of where I am in the cycle of the beat. All right. I guess I'm at 35 minutes, so I've got one more chunk of this presentation to go. And so I guess I'll run a little longer than I expected. But I guess to bring all this together, the idea of covert auditory active inference, which is to say active inference for controlling my actions, but without acting, is really just the same as saying auditory predictive processing, but using the motor system. And so this kind of gives us this account of why the motor system is what's doing this, this kind of predictive processing for the beat. I've got a preprint that is doing some mathematical modeling of this kind of process of phase inference based on event timing. I won't go into that now, but if anyone's who's interested in some of those details, I encourage you to look it up. I recently posted a revision. Okay, and so for the last piece of this presentation, I want to look at the role of the basal ganglia. And my motivating question here is now, is the supplementary motor area an oscillator, something that really just tracks a phase and gets driven bottom up by these auditory events and then adjusts? That kind of modeling framework has been used pretty extensively to talk about things that entrain to other things. And to a certain extent, the data supports that firing rates do evolve in SMA through local interaction. So it's like it's keeping sort of a clock. And those local interactions are driven and affected by sensory input. So it's a little like a forced oscillator. But in another respect, it's not. And it's been shown in monkeys that the shape and speed of the trajectories in SMA, these firing rate trajectories, change based on top-down input. So based on the task that they're doing and what they expect. And so it's not just this sort of autonomous ticking of a clock that gets perturbed, but instead we can have these very flexible phase estimate processes. We are flexible for tempo, of course. We also have flexible expectations for what's going to happen in between beats. You know, we can expect triplets, we can expect duplets. We're flexible about the patterns we expect to hear over multiple beats. You know, they may come in groups of 2. We may expect things to repeat after 4 beats. In other words, we have metrical expectations. And so I think that's where the basal ganglia may come in. The classical view of the basal ganglia is that a pathway through the basal ganglia takes cortical input and uses that through sort of this disinhibitory pathway. Cortical input can cause the striatum to inhibit a region called the globus pallidus, which then inhibits a region, inhibits the thalamus. The effect of this is to disinhibit specific selected motor plans. And that's the disinhibitory influences on supplementary motor area, also on premotor cortex, also on primary motor cortex. And so this classical view says the direct pathway is taking cortical input and selecting a motion plan. The active inference perspective on that would be that the direct pathway is integrating context to select a set of predictions, to select a set of proprioceptive predictions to actually execute the movement, or also to select a set of auditory predictions. So predicting the whole feedback from the selected action. And so I hypothesized here that basal ganglia may be establishing expected tempo for the next beat cycle in the same way that it has been hypothesized to carry a velocity reference signal that's transmitted in order to help control the selected action. There's a good review here that suggests that the basal ganglia is indeed controlling the velocity of the selected action. It may serve to create those flexible expectations between beats in the same way that we might expect different actions to have different auditory feedback. And it may mediate expectations over longer sequences of beats in a similar way to the way that it seems to play an important role in sequencing actions. So doing one action may serve as a cue to help the basal ganglia select a next action. And so it can then create these sequences that have been studied in mice in particular, or rats, I guess. And analogously to that, I'm hypothesizing that that its selection of one pattern of activity in SMA may then inform its selection of the next one, creating these higher order structures and linking these, one loop in SMA to the next. And in particular, metrical structures in rhythms are hierarchical. And there is good evidence very recently that basal ganglia is representing hierarchy in sequences of actions. And so this may be a natural structure for handling hierarchy in predictions. And so this is a sort of illustration of this hypothesis. Basal ganglia's input to SMA may be laying down the track for each cycle. And so here's this picture in monkey SMA that we looked at before. And so predictive basal ganglia input can set conditions in SMA to determine the duration of the next cycle. So make a loop that lasts 500 milliseconds, and SMA would do that. It could also then help to establish this higher level structure. And so basal ganglia input would then encourage it to make a second loop and a third loop, and also to slightly offset one from the next in order to represent the fact that I have slightly different predictions for loop 1 and loop 2 and loop 3. And to create this hierarchical structure as well. So maybe the fifth loop would be represented very similarly to the first one, based on this basal ganglia managing the hierarchical structure of these predictions. And so bringing all this together into a complete hypothesis, the SMA and the basal ganglia may be working together to infer and maintain an estimate of the phase of a sensory cycle or a motor a cycle in my movement, based on auditory event timing, and based on temporally patterned expectations that are then projected by the basal ganglia, selected by the basal ganglia, including expectations for the duration of the next cycle and the hierarchical position of the next cycle. And basal ganglia may then be telling premotor cortex what to expect to hear during that next cycle and establishing expectations for what happens between one beat and the next. And all of this estimate of the phase of the cycle in supplementary motor area can then be used for the purpose of predicting auditory events. So I've got a couple more slides on Parkinson's disease. I'm sensitive that I'm going over my projected time. But in Parkinson's, degeneration of dopaminergic signaling in basal ganglia causes a lot of the symptoms. And that dopaminergic signaling is really important for action selection and initiation. It's been observed that beat-based timekeeping and its perceptual benefits are impaired in Parkinson's disease, and that in particular beat-based rhythm perception is linked to the effects of rhythmic stimulation on gait. So all of this is saying that this picture may have real implications for Parkinson's disease. And my hypothesis is, this is not totally set. I've been thinking a lot about this and trying to figure out what to believe, but at this moment, my hypothesis is that rhythmic auditory stimulation is effectively circumventing the influence of the basal ganglia. It's setting up this cycle of phase estimation in supplementary motor area without basal ganglia help, based on sort of these very default expectations of just things happening on the beat at a default tempo, at something that's very close to the person's preferred tempo. So it may not need the help of these flexible expectations from basal ganglia in order to create this cycle in supplementary motor area that can then help control rhythmic action. And so some predictions from this would be that Parkinson's patients experience metronome without the same extent of metrical hierarchy that it would be created by the basal ganglia, and also that they show reduced tempo flexibility. And some questions raised by this that could be answered through modeling, and that I'm intending to do in the near future, is how can this network learn to make appropriate phase corrections given flexible expectations? And I think recurrent neural net models might be able to start to answer that question. And also the specifics about basal ganglia disorders and how they lead to specific rhythmic and timing impairments. And I'm also thinking that detailed neuronal models could start to help answer those questions. And I've got a lot of questions about the role of dopamine in this process, but I won't bore you with those. Thank you so much for listening. And also thanks to Ani, who started me down this wonderful road that I think will probably take the rest of my research career to reach a satisfying point in.
Thanks a lot. That's very interesting. I'm sure we have a lot of questions to ask. I should not begin because that would be a bad thing for me to do. Someone else has got a question. Anita is very impressed.
At least based on a thumbs up there.
Yes, Noemi is also very impressed. They're the only people who worked out how to find the clapping button.
Yeah. Feel free to use your actual hands. I like to
Yeah.
do this or this with people sometimes. Just put it up in the same corner.
Too. Okay. So any questions? Yes, questions.
Yes, I would like to ask something. Thank you for this very interesting talk. I'm wondering, how do you explain the improvement of movements in Parkinson, in the Parkinson patient just by listening to music? So the video you were showing, do you have a neurophysiological explanation for that?
I mean, so I think that's sort of extrapolating from this, the idea that rhythmic auditory stimulation, which could be in the form of a metronome or just something that's beat-based, beat-based music, could help entrain supplementary motor area, could create this like cycle where it's estimating the phase without as much basal ganglia input as it would usually need, as long as there's very clear sensory timing input to establish that representation. And then that supplementary motor area representation of phase is the same representation that gets used here to represent my phase in an action. And I think the difficulty in initiating actions in Parkinson's may be closely related to the difficulty in effectively getting SMA running, creating some kind of representation of where I am in the process of initiating an action. Supplementary motor area often shows preparatory activity leading up to an action. And I'm starting to view that now as like, I've made some kind of estimate of where I am in the course of approaching and then initiating and then continuing an action. And just, once SMA has this cyclic phase, then the brain knows exactly where you are in that progress. I am close to initiating an action. I am initiating it. I have just initiated it. And so I think that the trick may be setting up that structure, that dynamic structure in SMA, which often requires basal ganglia input, but can also be done through, by sort of jump starting it based on giving it the kinds of sensory data that it usually uses to establish and correct that representation. I'm not sure that was as articulate as I was hoping to be.
Yeah, sure. May I ask another question? So what is known about the neural connections between the SMA and the auditory cortex? So in the other and is there also a connection to the visual modality? So can this also be triggered by, for instance, flickering lights or something, or is this?
Yeah, hold on. I'm moving around because but I don't think I actually have the best picture for that. But the dorsal auditory pathway is sort of the the connection from the auditory cortex through parietal cortex to premotor and supplementary motor. So according to Ani's work that has reviewed his vocal learning hypothesis, in humans, that pathway is strengthened. And that is my sort of going hypothesis as to how auditory event timing is getting used to update phase in supplementary motor area. We do have connections that run from visual areas up to the same stream, the dorsal stream. But I think the strength of those connections and how much we rely on those varies a lot depending on the organism and how it controls its own behavior. And I think that humans just use less visual timing information to control behavior, and that's what would be carried by that visual stream. And I think to a greater extent we use auditory timing behavior to control our actions.
So that's quite interesting. And do you also see some kind of lateralizations, or is there some hemispheric dominance, for instance, of the left?
That's a great question. I think that there is something on that in the fMRI data, but I have not really focused in on that, so I don't think I can answer that question.
Thank you very much.
I have a question about the
Yeah.
relationship between dementia and Parkinson's. So
Ooh.
with dementia patients, often they're sitting all day not saying anything, and they're very disconnected to the world. And when you play music, especially music that they used to hear when they were a teenager or young adult, they suddenly become active, and suddenly they can communicate, and there are kind of quite remarkable things happen you see in YouTube videos, the amazing power of music for dementia patients. And when I see the guy you showed in the video who's suddenly walking just because he's hearing music, I wonder if is that because of the rhythm of the music, or is that because of something more general about music that enables old functions to start working again, that somehow overcomes degeneration in a general kind of way?
Yeah, I think that's a great question. I think that the fact that Parkinson's patients can specifically walk along with the beat, and that there is, I think, that the gait facilitatory effect seems to depend on rhythmic structure and seems to be entrained to rhythmic structure, suggests that it really is specific to rhythm. But I mean, you're absolutely right that music can have these massive neurological effects that are not related to rhythm. And I think that maybe then as you look for that, you start to want to look to the hippocampal formation, and the other ways in which music can establish certain contexts, and then that can bring you back into that contextual brain state. So yeah, I don't think I have much meaningful to say about the effect of music in dementia, which I agree is remarkable.
I have this idea about fear, the fear of doing something wrong. So if I've got dementia or Parkinson's, in all of these interacting with other people or walking, I'm constantly afraid of doing something wrong, and therefore I don't do anything. It's kind of got the effect of freezing. Mm-hmm. You can't actually measure fear. People aren't saying they're afraid, but the effect of music is to somehow suppress fear. Is that right? Is that a possible kind of global way of looking at it?
Give me a moment. So I think the predictive processing angle, to try to bring that together, like if music makes you move and act, then according to the predictive processing framework, it's because it causes you to expect to move and act. It causes you to expect yourself in that context to move and act. And whether that's through an association between, just like every time I hear music, I always dance. So now I dance, or whether it's through establishing a different context, that like when I hear this music, I believe myself to be in a safe context. I think there's a lot of different ways that could happen. I definitely hesitate to attribute these like direct motor effects to a lack of fear per se, but inhibition, maybe, that may be a meaningful way to think about it. Yeah.
Thank you.
I think that's a really interesting thought.
Thank you. Next question, please.
Sure.
Yeah, Andrea?
Yes, am I audible?
Mm-hmm.
Yes, okay. Well, thanks so much, Jonathan. I think it was a great talk. Very complex questions and very complex concepts, and I think you did a great job by kind of taking us and providing us with a coherent story. I wanted to go back a bit at one of your points in the introduction when you mentioned simulation theory and the concerns that you have over this approach. If I understood correctly, your concern, this was mostly related to the role of imagination. So you're saying when people simulate something, they should create a sort of explicit representation of what they are simulate by, for example, imagining what they're doing to put themselves in a certain context so that they would feel as if they are doing the same thing that they are simulating. Mm-hmm. But I wonder if this critique mostly applies to the previous approaches to simulation theory. For example, in 2002, but then so-called embodied simulation theory kind of posits instead a sort of pre-reflective simulation. The idea is that it is your cognitive system that simulates without any kind of, imagination or explicit representation of what you are simulating. It's just, a matter of your motor system being active as if you are actually doing what you are instead witnessing. So I wonder if there is perhaps a deeper connection between the story that you provide between that you explain in terms of for example, expertise in terms of minimization of prediction error and expertise in terms of building up a repertoire of actions that can be simulated. So do you see that there is perhaps a connection between these 2 points, or you see instead a stark barrier?
I think that the way I characterized my objection to simulated actions may have, I definitely stated that I was concerned about, the specificity and such. I think, if I dig right down to it, my real objection is just that I don't feel like simulated action was well defined. And I think that may be in the literature that I've been reading about this that I'm citing here, but it may be you're drawing on a literature that actually creates a better picture of what it means to simulate an action or simulate something. So yes, I think that if you can provide a satisfying definition for a simulated action, that I'm happy to call. I guess so I see what I'm doing as building on action simulation for auditory prediction. And I'm not using the word simulation because I haven't found it all that useful. But like, if you want to call this, wait, I'm trying to find the right slide. This one, where I'm doing the loop making thing here. Like, if you want to call this action simulation, then and like, make a connection between the concept of simulation and the production of these temporal intervals that have no particular motor output associated with them, then I could see that being a meaningful connection there. I guess maybe in a way what I'm trying to do, but though it's not the language I'm using right now, but I think what I'm trying to do is to try to provide a definition for what a motor simulation might be at a neural level, and then try to say, like, okay, conceptually, I guess the simulation means that we have some sense of where we are in the progress of a, quote, movement, even if we're not making it. I guess that, so I don't see any deep conflict with the ideas of simulation. I just think it's a matter of juggling the concepts well.
Thanks. That really helps. May I ask just another quick follow-up on that?
Yeah.
Thank you. So so for example, if we for the simulation story, perhaps can also have an account of emotions by for example, by simulating an action, being that simulation something very visceral, you can also see very strongly the connection, for example, with the emotional or the affective sphere that would somehow permeate that action. Mm-hmm. But I wonder, what kind of story would a predictive coding approach have with regard to emotions?
Right. So I mean, that would have to take me out of the predictive coding of rhythm and phase in particular, and look, more generally at predictive coding. I mean, I think they usually discuss predictive coding or emotion is a type of interoception, where you're interpreting your body signals to imply that you are in a certain type of context, yeah, I'm not. I don't think I have anything ready that would really link the rhythmic picture of the rhythmic story there to the emotional predictive processing.
I wanted to ask you, Jonathan, would you think that you need to disentangle the rhythmic dimension from the emotional one, or you think, I mean, not now, but of course, perhaps in the future, we can build up a story that would also have an emotional somehow framework to capture the emotional part of rhythmic perception and auditory.
Yeah, I guess speaking as a musician, I feel like there's kind of, when you're looking at just rhythm, the key emotional dimension is from like fast and intense to slow and laid back, right? And I guess in that respect, I think there is a pretty clear predictive coding story, which is when I make fast actions, it is usually in a intense context. And so as I hear a fast rhythm, I'm interpreting that in the same way that I'm would interpret myself producing a fast rhythm. The supplementary motor area doesn't see any meaningful difference between those situations. And so I could then interpret that to mean that I'm in an intense context and I need to do all of the bodily things that I need to do in order to go there. Is that sort of what you were thinking?
Yeah, thanks. No, that really helps because I'm not really, I'm not really an expert on predictive coding. I'm trying to delve into it, but so your talk really helped. So thanks so much.
Sure. Yeah, if you look up interoception and predictive coding, then there's a lot of people that are just recently starting to write more about emotion in predictive coding.
I have another question since we have another minute. My other question, I'd like to go back to the slide where you had on the one side the motor commands and on the other side the proprioceptive feedback. And it goes up and down and around and around.
Oh, wait, this one or this one?
This one, yeah, that's right. Yeah. So I'm interested in the role of learning and the development, the ontogenesis of this system. So you referred to a paper by Wang et al. Called Flexible Timing by Temporal Scaling.
Yeah.
Where they did some experiments with primates and some motor control things where they found that there was a lot of learning going on at the animals were able to learn kind of uneven rhythms or some unusual timing profiles.
It was just learning different intervals in particular, but go ahead.
And it suggests that this whole system is quite flexible and learning plays an important role. Is that right?
Yeah.
And so the question is then, when does it start? Right, the chicken and egg question. How much of this is nature and how much is nurture? When does this system get kickstart?
Yeah,
because you can learn it in a musical context, right? If I go to clubs every Saturday night and I dance to a rave or something, I'm going to train the system. And somehow the system also needs to be trained in a non-musical context, in other words, for it to kickstart itself.
So that's a wonderful question. There's a fantastic paper. I haven't seen anything else like it, but Jennifer Kuhl wrote this wonderful paper on, and I'm trying to remember the title of it, but the way that our sense of time is informed by our own and learned by our own actions. So I think just to go out on a limb and try to sort of extrapolate from this. Actually, okay, so two things. One is I think that flexibility is very much in the way that the basal ganglia is sending these flexible expectations to SMA in order to shape its activity. I think that what we have right here has not a lot of flexibility really built in. Like you could do this and just learn metronomes and that's it. But I think that the connectivity between basal ganglia and SMA and the way that SMA responds to a particular set of inputs, I think that must be learned over time. And I imagine that a lot of it is bootstrapped by just making periodic actions myself. My 16-month-old son, does a lot of banging on things and, doing it with different levels of intensity. And I think that kind of cyclic action is just using my feedback from my own action as a cue to initiate the action again. There's no real phase tracking that's necessary in that. You don't need to know where you are in the action to do it. But as you do it, you now find that like there's predictability in the feedback that I get. And so I think that you sort of act first and then you learn what becomes predictable in the feedback from that action. And that starts to bootstrap this process of like estimating where you are in the action and being able to adjust it in real time and being able to slightly modify it in tempo. So you're learning from the things that you've done. And then I think that like that kind of learning through action then generalizes to learning auditory structures, because as I banged on this thing, I learned what it was like, what kinds of input I needed from basal ganglia in order to accurately estimate when I was going to hear the next sound. And so when I hear something like that, then that kind of input from basal ganglia is what I need in order to make those predictions, even if I'm not the one who's causing those things myself. I think the question of learning this is a deep and interesting and fun one. And I'm in my modeling work. I think I'm maybe 2 or 3 steps away from those. Each step's going to take multiple years, but like I can sort of see trying to go in that direction.
Thanks. That was a great answer. I enjoyed it. Is there someone else asking a question? Come on, folks. Adrian has a question.
Yes, indeed. Yeah, thank you very much for the talk. So just a comment. Yeah, I have several comments, maybe just regarding the learning process, which Richard just mentioned. I mean, there's a lot of literature, connected to ideomotor theory and common coding and so on, motor babbling and so on, on this on establishing these links. So yeah, and they go quite hand in hand with the predictive processing framework. Yeah, but it's maybe the one question I have is connected, because I was thinking, using the proposed model, the model you proposed, where exactly would be the boundary between like the predictive maintenance of the beat and the start of inferring where the regularities are in the beginning? Because for example, when the tempo is changing, then you're getting prediction errors. Of course, if you have no idea that there should be regularity, probably you don't have any prediction errors, but because of the cultural context, you have prediction errors that there should be regularity. So do you just simulate like movements?
What you're asking is a wonderful question. There are some details in what you were saying that I kind of want to fixate on, I guess. One is that if you don't know anything, then there's no prediction errors. If I'm outside a cultural context or something and I'm just hearing something, I think one trick to understanding the whole predictive coding world is to understand that there are always prediction errors. Anything that if most of the time I spend not hearing clicks and I hear a click, there's a massive prediction error right there. But I think that's important, because establishing a underlying structure is a way of minimizing prediction error. And so when we hear something that we don't know to be structured, we start searching. We start trying to find ways to predict when those darn clicks are going to happen, in order to then be able to suppress or at least know what's going to happen, to minimize those prediction errors. Now, I'm struggling with this a lot. I feel like I have a much better picture of how we maintain these structures than how we establish them in the first place. And people like Ed Large have this idea that we can extract a resonance from a stimulus that then can like set up that structure in the first place. I don't agree with that, but I don't have a great argument against it. I think that what we're doing is we're recognizing. I think that our auditory system has a certain amount of buffer. We can hear temporal patterns and just say, does that match a temporal pattern I recognize? And so I think in situations where I hear a complex rhythm right away, a big part of what may be happening is I have heard that complex rhythm before, and here is where the beat was, or I'm hearing a complex rhythm and there's a kick drum and it's telling me where the beat is, which I can then use as training in order to recognize that complex rhythm later on without the kick drum. I think that we're probably doing things like bootstrapping like that and recognizing, and that may play as big a role in extracting the temporal structure as anything like, resonance, recognizing the tempo. If we hear, say this, dum, bum, 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 bum. Like in order to go from, which immediately sounds like an isochronous sequence with a specific tempo, and to then recognize that when we hear that little, other thing, that actually means we were at the wrong tempo entirely. There's a faster tempo and an underlying beat that it wasn't immediately apparent. Like, that doesn't seem like a resonance phenomenon to me. That seems like, oh, I've heard that rhythm before with a kick drum. I know where the beat is, once I've heard a cycle of it, and I can do that now. I know what the tempo associated with that is. but I wish that led to more elegant modeling. I'm sort of trying to like go in that direction and try to do something meaningful with that as well. It's a great question.
Yes, so you probably would also say that like inferring a beat in music is something different from inferring it in a other context. For example, there are these experiments with noise bursts and so on.
Well, right. I think that, you know, whether I'm hearing a clave doing it or I'm hearing a noise burst doing it, if I'm hearing a clave, I can use the association and say like, oh, you know, this is probably playing on the you know the one, the you know, the and of two and whatever. And so yeah, I think that perspective then explains why you can enculturate so much to this process, and you can you know, some people can extract a beat very, very quickly in some contexts, and you know what rhythms we're used to will have such an effect on that. I think that's, you know, in Ed-large, I think would explain that in terms of the connectivity of the network that we're trying to find resonances in. But I think it's not necessary to go that complicated. I think that, you know, we've got an auditory buffer where we're using the rhythms that we hear and associating it with past experiences, listening experiences. And based on that, we're saying, oh, there's actually a model for this that works really nicely. Here it is. And now we've got the phase, and we're just maintaining it based on prediction errors.
Okay, so basically, you would say that your model could be expanded without any need for a special beat induction.
Well, what it would be is, and I actually am sort of going down this road. I've got the beginnings of the mathematical picture of it, but we're looking at different possible templates, and we're evaluating those as we listen. And we're saying that, like, okay, based on what I've just heard, it seems likely that the structure of expectations that is relevant here is this one over this one. And as I listen, that may get reweighed. You know, it may be like, oh, actually, I'm listening to this kind of template with triplets. And so I mean, this thing is not done yet. I think that I'm not taking into account the fact that we have an auditory buffer very effectively yet. I'm trying to do this sort of in real time. So there's like a lot of work to do there, but I think that's the kind of language that I would use, you know, reweighing these different possible things that I've been exposed to. You know, I've got a strong prior that what I'm going to hear will have duplets, but then I get some contradictory information and I instead try to pull up the triplet template. And that then takes into account this enculturation and past experiences with different types of rhythms.
Yeah, thanks. Yeah, that's really interesting.
I think we're coming to the end right now. Is that right? No more hands waving down there. So Jonathan, thanks very much for your talk.
Yeah, thank you guys for the excellent questions. I think you hit like most of the interesting stuff that I didn't try to cram into here, and that I haven't really fully, you know, worked up into a presentation.
That's good. I believe that Andre is clapping and not raising his hand. Is that right? He's clapping. Yes, that's right. So next week we have Luc Nees, who's a postdoc from Belgium, from Ghent in Belgium, who's come to our center just recently, a few days ago. He will give a talk about his research, and we have a full program of talks every Tuesday after that, which you can see on my webpage. Thanks everyone for being here. Who would like to say the last word?
Thank you.
That's good.
Thank you.
So wish everybody a pleasant evening.
Bye all.
We'll catch you again.
Sure.
All right. Bye.
I'll have a pleasant evening eventually.
Yeah. Thanks. Bye.
Bye.